So a nonpolar molecule will be able to pass through the phospholipid bilayer with its hydrophilic head, but its nonpolar fatty acid tails are acting as a barrier. So the real problem is not the size, it's the polarity. So the polarity is fine for here, but it's not fine to get past that point. It can't get past the nonpolar. Polar molecules can't dissolve and bypass the nonpolar barrier that is the fatty acid tails here. But this nonpolar molecule can pass through. These hydrophilic heads, they'll just move aside. They're perfectly fine doing that. This nonpolar this nonpolar molecule will be able to bypass these nonpolar fatty acid tails just fine. But this polar molecule will not be able to bypass these tails. And that's the key determining factor here. Polar molecules will not be able to cross a plasma membrane without assistance. That assistance will need to come in the form of some sort of transport protein. And we'll talk about those soon. So, now, some molecules that can diffuse through cell membranes. We will have oxygen, which is a nonpolar molecule. It will be able to diffuse very quickly. It is both small and nonpolar. So it can diffuse just fine through the plasma membrane barrier very quickly. Carbon dioxide is nonpolar, but it is also very small, and it will diffuse quickly. Water, however, water is polar. Water, if we recall, Unit 1 stuff, that is a polar molecule. It has a negative charge here and a positive charge here. Delta positive and delta, oops, yeah, that looks terrible, but it'll work, and delta negative up there. The partial negative and partial positive charge here makes it a polar molecule. But here's the deal. Water is a tiny molecule. It is way smaller than the fatty acid tails. So guess what? Water is quick. So water is fast enough that it can bypass this nonpolar membrane. Bypassing this nonpolar membrane gives you the ability for water to move through the partially permeable membrane and into and out of the cell, but not quickly. It will take time. And eventually we'll see the consequences of that in the need for aquaporins later in Unit 4. So that brings us to the idea of facilitated diffusion. But, well, I suppose we could talk about aquaporins now, because that is an idea of facilitated diffusion. But I'm going to actually start off by talking about glucose amino acids, because those are large polar molecules. Large polar molecules like glucose amino acids, they are not going to be diffusing across that membrane. Not normally. And very, very polar molecules, like ions, like sodium or chloride, they're not going to be passing by themselves. So molecules, they will need to pass through protein channels instead. This is facilitated diffusion. The diffusion of these molecules will still be passive. It will still be down a concentration gradient from high concentration to low concentration, but it will be facilitated by a protein channel. So I will have my molecule, I will have my barrier, excuse me, let me actually draw this correctly for a change. I'll have my barrier, all right, but I'll have to have a channel set up. In order to allow it to cross. So this is diffusion facilitated by a channel. Otherwise, it would not be able to cross that nonpolar barrier. So, because this is a charged particle, it cannot cross the nonpolar, but it can cross facilitated by a protein. It's still passive. It's still moving down a concentration gradient from high concentration to low concentration. But because the molecule is too large or too charged to diffuse on its own, it will need a transport protein to help it along. This is when it does not pay to be large or charged. Now, large or in charge, excuse me. My jokes fell flat. What a surprise. All right. Now in our fluid mosaic model, I have a transport protein right here. If you remember what it looked like, there you go. Now, this is facilitated diffusion again. We have equilibrium of our red dots. We're still at equilibrium with our red dots, but now we've added a protein channel. This protein channel is large enough for our blue dots to diffuse through. They can pass, and they will, until we reach equilibrium of blue. Now we have equilibrium of blue and red. Remember, equilibrium is no net movement of molecules between a partially permeable membrane. So we have no net movement. And once again, a diffusion only applies to one molecule at a time. Only one molecule at a time. So the diffusion of blue only matters to the diffusion of blue. The diffusion of red will not be affected by blue's movement. Now, facilitated diffusion is still a passive process, and this is a reiteration of a slide we had before. So now we can move on to osmosis. Osmosis shares a lot of properties with diffusion, but unlike diffusion, where it is the movement of solutes down their concentration gradient, osmosis is the movement of the solvent down its concentration gradient. So osmosis is the movement of water. Water is the universal solvent here. And you can make the case that osmosis can apply to more things than just water. But for our current understanding and for our current level, osmosis is only going to be dealing with water. And that's all we're going to need to know for right now. We can add more stuff later in future. That's a problem for future us. Future us has other problems to deal with. All right, current us has these problems. So we're going to have concentration of water molecules, and we're going to call that water potential. Concentration of water molecules is water potential. So remember, concentration, I always abbreviate it like this. Concentration of X. But now that I have, when I have concentration of water, I'm going to call that water potential. I'm also going to be able to abbreviate that as the Greek letter psi. Little trident, like Poseidon. Alright. King of the ocean. If this were ancient Greeks. Alright. So, water potential. An area of high water potential, water will move by osmosis from an area of high water potential to an area of low water potential across a partially permeable membrane. That is osmosis. That is osmosis. So, now we're going to treat these red dots as water molecules. No longer are we treating red dots as individual solute particles. We're treating the red dots as if they were water. And the blue dots are going to be sugar. Now, I'm going to do something crazy in these videos, and you're just going to have to go along with me. I'm going to call everything dissolved in water salt. Everything dissolved in water is salt. So, My salt over here, I have a high salt concentration and a low water potential. I have a high water potential and a low salt concentration. And I have a partially permeable membrane here. It's permeable in such a way that water may pass, but salt may not pass. So when the salt passes through, when the salt is stuck on this side, what's going to happen? What's going to happen is that the salt can wiggle around all it wants on its own side, and the water is going to follow the salt. So the water is going to move from an area of high water potential to an area of low water potential until it reaches equilibrium with water. And it's going to be an equilibrium concentration, an equilibrium water potential. When water potential is equal on both sides, when water potential is equal on both sides, psi side A is going to be equal to psi side B. That is equilibrium. Now that is the water concentration. Now remember, this is how much water do you have versus how much stuff do you have dissolved in it. So this is a ratio. It's a ratio of how much salt to how much water. So this is effectively salt concentration over water of A versus salt concentration of B over water of B. These numbers don't have to be the same. You don't have to have 50 and 50 and 50 and 50. You can have 10 and 50 as long as this is also 10 and 50. Or as long as this is also 1 and 5. The ratio's got to be the same. It's got to be 1 to 10 and 1 to 10. 1 to 5 and 1 to 5. If this is 2 to 10 and this is 1 to, and this is, if this is 2 to 10 and this is 10 to 50, that's the same ratio and that's fine. As long as the water potential is equal, we are okay and we are at equilibrium. So water will follow salt. It's going to follow the high salt concentration. Water follows salt. Big graphic right here, just right here, middle of the screen, right there. All right. Now, here we have an example of a cell water can diffuse across this membrane. We already know water can diffuse across this membrane. Water is going to try to follow salt. Here's our salt. Here's our salt. So water is going to follow salt from the outside, the area of high water potential, to the area of low water potential. The area of high water potential to the area of low water potential. Water follows salt. So what's this going to end up looking like? It's going to end up looking like this. This cell is going to swell, and this cell is going to shrink in order to find equilibrium in that cell. The water will try to leave the cell to follow the salt until it can't anymore or until it equalizes and finds equilibrium. Water will try and enter the cell until it can't anymore by destroying the cell or it finds equilibrium. Now, let's talk about what that equilibrium concentration ends up actually being, because we'll take a quick aside for sodium and potassium. There is a high concentration of sodium outside the cell and a low concentration of sodium inside the cell. and a high, and it's the reverse for potassium and calcium. So that is maintained by active transport, but we're going to discuss that in a moment. We're going to actually take an example of facilitated diffusion, and we're going to talk about a concept that's going to come into play very intensely in Unit 4, chaining concentration gradients. So here is an example in the intestinal tract. We have glucose, because last I checked, we tend to eat bread as a species. And that bread is made of carbohydrates, because, you know, that's why, that's what we eat, man. And so it breaks down through the action of the enzyme amylase into glucose. That glucose is too large and too charged, and too large and too polar to enter into the cell on its own through diffusion. So it has to enter through facilitated diffusion. Now, when it enters through facilitated diffusion, there must be a transport protein on the one side. So there's a high concentration of glucose in the gut tube, and then there's a low concentration inside the cell, the intestinal cell. So this is your high concentration of solute. This is your low concentration of solute. Then you've got another of those same transport proteins here, which leads down to the blood. You're going to have low blood glucose, even lower concentrations of glucose in the blood than in the cell. So from medium concentration to low concentration. So from high to medium to low. Glucose is going to diffuse down its first concentration gradient from high to medium, then down its second concentration gradient from medium to low. But then, what if this reaches equilibrium? Well, the good news is that your blood is flowing. If it's not flowing, you might want to go see a doctor right about now. That it's okay, you can pause the video, just press the space bar, and if the screen like suddenly jumps down real quick, press the K button. That actually works. Yeah, and then you go see a doctor. We'll be here when you get back. I'll wait. Now, the blood flowing through this vessel is actually going to take away that high concentration of blood glucose, and it's going to return low blood glucose. All right? And now you've maintained your low. So you have high concentration to medium concentration to keeping that low blood concentration of glucose. And this is maintained at medium by that flow. This is maintained at high concentrations of glucose by you continually eating bread. And that's how you gain weight. So let's talk about lactase non-persistence, as I prefer to call it. So in lactase non-persistence, also known as lactose intolerance, the disaccharide lactose, which is galactose and glucose, which is a beta 1,4 glycoside,